And here is the location of the Port and the Airport Research Institute I used to work. And now I'm working here right now. And the Hasaki Coast stretches about 16 kilometers from the port of Kashima to a river mouth here. And the study site is located here. And at the Hasaki Coast, we have the 400-meter long field observation pier as shown in this photo. And along this pier, including the land area, we measure the beach profiles at 5-meter intervals. And in this study, we use the beach profile data weekly obtained over the 28 years from January 1987 to November 2014. And here is the superposition of the measured beach profiles. And this green line shows that the mean beach profile, and near the shore, the beach slope is about 1/30. And at the tip of the pier, where the water depth is about 5 meters, the beach slope was about 1/120. And the sediment diameter is about 0.2 millimeters. And our target is here and the backshore. And the dotted line of this figure shows that the beach profile measured at the start of the investigation period, January 1987. And thin solid line, this one, shows the beach profile measured at the end of the investigation period, November 2014. And our investigation area is here. And in this investigation area, the elevation changed 1 meter to 3.5 meters, and on the average, 2.5 meters. And the lower figure shows the topography around the study area. Upper side is the seaward side. And as shown in this figure, the topography around the study area is relatively uniform along shore. So this indicates that we can assume the gradient of the longshore aeolian sediment transport rate is close to 0. So we neglected the gradient of the longshore aeolian sediment transport rate on the beach profile change in the backshore. And that these photos shows that the vegetations in and near the study area in summer. And the vegetations grow in summer. And these are the 3 main species that occupy the study area. And these kind of the creeping grasses grow in summer, including the Japanese sedge, sea bindweed, and American dune grass. And this figure schematically shows the beach profile in and around the backshore. And the study area, investigation area, is located here, from where the seaward distance is minus 65 meters, and this is the seaward limit of the vegetation, and to where the seaward distance is 115 meters, and the point of the beach profile measurement. And 10 meters landward of the investigation area, dune is located here. Well, in the previous studies to investigate the morphological changes in the backshore and dune, not only the winds, but also waves are considered. However, in this study site, the waves rarely reach the investigation area, just once or twice a year, and never reach the dune here. Only the exception is the 5-meter high tsunami in the 2011 Tok earthquake. At the time, the tsunami reached up to this point. But except for that, the waves rarely reach this investigation area. And this figure shows that the time series of the landward limit of the wave run-up. Well, the data is a little bit old from 1995 and 1996 and a little bit limited, but well, the seaward limit of the investigation area is here. And as you can see, the waves reach this area, the investigation area, twice in 2 years. So this means that the waves really influence this investigation area. And the fact that the investigation area was not heavily influenced by the waves is partially supported by the fact that this area, the investigation area, was entirely covered by vegetation, which cannot grow in the influence of the waves because of the salt water. And again, this is a target of our study. And the upper panel shows that the weekly average volume change rate, and the lower panel shows that a cumulative volume change from the initial profile. The volume of the backshore increased almost monotonously with time, but the increased rate seems to slow down toward the end of the investigation period. And from the next slide, I'd like to explain that the characteristics of the environmental factors, such as winds, rainfall, and the vegetation. And this is the coordinate system used in our study. And in the cross-shore direction, the landward wind velocity is defined to be positive. And the direction of the winds from the north is defined to be positive. And this slide shows that the monthly averaged values of the wind direction, wind velocity in the upper panel, and cross-shore and along-shore wind velocities in the lower panel. As shown in the upper panel, the winds mostly come from the north, and the wind velocity was large from February to April due to the developed extratropical cyclones, and also from September to October due to tropical cyclones called typhoons. And in the cross-shore directions, the landward wind velocities are predominant. This probably induced the continual accumulation in the backshore. And this slide shows that the variations of the yearly average values. Compares with the variations of the monthly average values, those of the yearly average values are relatively small. And this slide is for the amount of the rainfall. The upper panel shows that the monthly average values, and the lower panel shows that the yearly average values. Well, as shown in the upper panel, the amount of the rainfall is large from September to October due to typhoons. And for the yearly average values, the values varied from 1,000 to 2,000 millimeters per year. And the average value is about 1,500 millimeters per year. As for the vegetation, the vegetation grows in summer as shown in the left upper photo, but disappears in winter, like this photo. And the lower panel of this slide shows that the monthly average ratios of the bare area, vegetation area. And the vegetation grows from May to September, but disappears from December to March. And from now on, I'd like to explain how to estimate the volume change in the investigation area. And here is the investigation area, and here is the seaward boundary, and here is the landward boundary. And the volume B of the backshore is estimated from the difference between the volume flux at the seaward boundary and the volume flux at the landward boundary. And when the winds blow from sea to land, the aeolian sediment transport rates at two boundaries were set like this. And here, Q is the aeolian sediment transport rate without vegetation, because the seaward of that investigation area, there is no vegetation. So this Q was set here. And at the landward boundary of the investigation area, R sub B was included. R sub B is ratio of the bare area because the sediments are transported over the vegetated area. So this parameter R sub B was included. And here, near the landward boundary, the wind fields may have been influenced by the volume. So to express such an influence, we added the coefficient C sub 1 here. And in fact, the ratio of bare area was differently treated the inside and the outside the investigation area. The reason I will explain later. And when the winds blow from land to sea, these aeolian sediment transport rates were set at the seaward boundary because the sediment are transported over the vegetated area. R sub B was included, and at the landward boundary, the different coefficient C sub 2 was included. And the reason why that two parameters for the ratio of the bare area were set is that left upper photo shows that the vegetation in 1995. And as you can see, the north of the survey area, the vegetation was removed. In fact, in 1994, the vegetation here was removed because of some other field measurement. And it took about 13 years for the vegetation to fully recover, as shown in this right photo. So the parameters for the ratio of the bare area was treated differently inside and outside the vegetation area, investigation area. And the lower figure shows that visually observed that ratios of of vegetation north and south side of the survey area. And this the slide shows that how to estimate the aeolian sediment transport rate without the vegetation. The aeolian sediment transport rate without vegetation is estimated using the cumulative formulas shown here. Here U prime is the friction velocity and U prime C is the critical velocity. And U prime and Z prime are the wind velocity and the elevation at a so-called focal point where the wind velocity is fixed. And here D is the sediment diameter, and we assume that the sediment diameter is 0.2 millimeters. And the K is a coefficient. And in the previous study, the K is reported to be 1 to 3. As for the rainfall, that we assume that the aeolian sediment transport rate is 0 during the 24 hours after the precipitation larger than 1.0 millimeter per hour. And here is a summation of that how to estimate the volume change. And the volume, aeolian sediment transport rate was assumed to be proportional to the square of the ratio of the bare area. This is based on the study of the Tsujimoto et al. For the non-equilibrium sediment transport rate. And here, Q sub NE is non-equilibrium aeolian sediment transport rate. And L is the distance. And this the change rate of the non-equilibrium aeolian sediment transport rate can be estimated from E, the pickup rate, and D is the deposition rate. And the deposition rate is expressed as the non-equilibrium aeolian sediment transport rate divided by step lengths or saltation lengths. And now that we assume that the saltation lengths and the pickup rate is proportional to the ratio of the bare area, and under the condition that at infinite distance, the non-equilibrium aeolian sediment transport rate reaches the equilibrium sediment transport rate, the equilibrium sediment transport rate is estimated like this, which is proportional to the square of the ratio of the bare area. And now we have three parameters, C1, C2, and K. And we determine these three parameters using that least square method, so that the error in the weekly average volume change rate measured and simulated becomes minimal. And the 20-year data set was split into two. The first half was used for the calculation, and the second half was used for validation. And here is the obtained parameter values. C1 was 0.58, C2 was 0.53, and K was 1.0. And this C1 value of the 0.58 is equivalent to the 11% reduction of the wind velocity. And the C2 value of the 0.53 is equivalent to the 12% reduction of the wind velocity, which seemed to be reasonable. And the K is 1.0. And as explained before in previous studies, the reported K value is from 1 to 3. So also the obtained K value is reasonable. So the obtained three parameters, C1, C2, K, seem to be reasonable, but the correlation between the weekly average volume change rate measures and the simulated has almost no correlation. The correlation is quite low. However, for the cumulative volume change, their model expressed by this red line simulated their measured values to some extent. The model could not reproduce this say steep increase. However, to some extent that the model reproduced that slow increase toward at the end of the calibration period. And as an index to evaluate the model performance, Breyer-Skill score is frequently used. And the Breyer-Skill score is shown here. And the B sub S and the B sub M is the simulated and the measured value. And the numerator in the second term is the error between the simulated and the measured values. So when that model perfectly matches the measurement, the BSS value becomes 1. And for model for the morphological change, von Rijn proposed a criterion. So according to his criterion, when that model set BSS value is larger than 0.3, the model is evaluated as reasonable at least. And this slide shows the root mean square errors, correlation coefficients, and the BSS values for the weekly average volume change rate and the cumulative volume change. Well, as shown before, that there is no correlation, so the model could not reproduce that weekly average volume change rate, but the model performance for that the cumulative volume change was not so bad. And from the next slide, I'd like to show the result for the validation process. And here is that the correlation between the measured and the simulated volume change rates. And as expected, there is no correlation. And here is for that the cumulative volume change. Well, in the first half of that validation process, the model will reproduce that the measurement, the continual increase. However, the measurement measured cumulative volume change did not have that increase and almost saturated in the second half, but the model could not reproduce such variations. And here is the statistical values. Well, although the model could not well reproduce that in the second half of the validation process, the cumulative volume change, the BSS value was 0.65. So not so bad. And to investigate that the causes, that the why the model could not reproduce that weekly average volume change rate, but reproduced that the cumulative volume change, we did the cross-spectral analysis. And this slide shows the results of the cross-spectral analysis between the measured and simulated volume change rate in the calibration process. And from the top, this slide shows the power spectral density, coherence, and phase. And as shown in the power spectral density, there are two peaks. This is for 1 year, and this is for the 6 months. And here is the 1,000 the days. That means that the 2.7 years. As shown in the middle panel, the coherence was high at lower frequencies, but it fluctuated at the higher frequency. Same results are shown for the validation process. The coherence was high at the lower frequencies, but fluctuated at higher frequencies. So we think that this is the reason for that the model could not reproduce that volume change rate induced by high frequency components, but reproduce that the cumulative volume change induced by the lower frequency components. And to investigate more the causes of the discrepancy between the measured and the simulated volume change rates, we listed the influence factors on the air sediment transport rate. The angle and the irregularity or gustiness, sediment size and its distribution, vegetation, beach width or moisture due to waves, and the moisture due to rainfall. These two are related to fetch length and beach slope, and the small scale features or micromorphology, including ripples, rock, dense vegetation. And the factors that are marked with the red rectangles are considered in our model, but the rest are not included in our model. And the discrepancy for that cumulative volume change in the second half of that the validation process may be the beach slope. Well, in the second half, the beach became steeper, and the relatively steep slope may have decreased the aeolian sediment transport rate. And in fact, the beach slope increased in the study area from 1/28 at the start of that investigation period to 1/16 at the end of the investigation period. And how to include the influence of the beach slope into the estimation of the aeolian sediment transport rate was proposed by several scientists, including the Iversen and Rasmussen, Lovink and Costas, and Hardesty and Whitehall. So that, and I think that including the beach slope into the estimation of the aeolian sediment transport rate should improve that the model accuracy. So in the next step, we will do that. Well, as for the fetch lengths, that we did not explicitly consider the fetch lengths in our model. This is because that we assume that the aeolian sediment transport rate reached the equilibrium state in our investigation that area. And the reported fetch lengths in the previous studies ranged from 10 meters to 200 meters, very wide range. And this figure shows that again, that time series of the landward limit of the wave run-up. And here is that the seaward limit of that our investigation area. And this one shows that the approximate average upper limit of the wave run-up. The distance is minus 25 meters, and here minus 65 meters. So this distance, 40 meters, is the average the fetch length in our study. And the 40 meters compared with the reported fetch length is larger than at least the minimum value of the reported pitch length, the 10 meters, and confirm that the 40-meter pitch length is enough for vegetation, for the aeolian sediment transport rate to reach that the equilibrium state. We calculated the crucial variations of the equilibrium and non-equilibrium aeolian sediment transport rates in the study area. And these are the formulae to estimate the equilibrium and non-equilibrium aeolian sediment transport rate, and I explained it before. And the 2 dB wind field was estimated using the Navier-Stokes and the continuity equations. And here is the result. And the right side is that the seaward, and right axis is that the seaward limits of the investigation area. And the solid cycle shows that the measured aeolian sediment transport rates and the non-equilibrium aeolian sediment transport rate is expressed by solid line, and the equilibrium sediment transport rate is expressed by the dotted line. The actually two lines are almost completely overlapped. So this result shows that the 40 meters of the pitch length is enough for the aeolian sediment transport rate to reach the equilibrium state, at least in our study site. However, that calculation was conducted under the assumption of the average pitch length of the 40 meters. And sometimes the pitch length reduced to 20 meters, and this reduction may have the causes the discrepancy between the measured and the simulated volume change rate. And also that discrepancy can be attributed to the small scale features, including rock densification as shown here, which are not considered in our model. The small scale features may locally change the aeolian sediment transport rates, and the integration of such kind of the local changes may lead to the errors in the volume change rate. Okay, let me conclude my talk. We developed a one-dimensional model for volume change of backshore, considering the wind velocity and direction, sediment size, precipitation, and vegetation in the process. And we calculated and validated using the 28-year beach profile data. The model originally produced that the cumulative volume change, but it did not the weekly average volume change rate. And this can be attributed to the presence of the small scale features such as densification and wreck, or small pitch lengths due to the large wave lineup. Okay, thank you very much for your kind attention. That's all. Anna, still.
Yes, thank you very much. Thank you very much, Josh. It was very good. Now I was just waiting to see whether Tommy was going to take over for the Q&A, but he was waiting for me to tell him to take over. So thank you very much. I enjoyed very much. There are a few questions in the chat, and I will let now Tommy manage them.
Okay.
Thank you for a really good talk. Okay, so we have a couple of questions.
Thank you.
Come up. So the first one is from Mandy Tran from UNSW. And her question is there an assumption that sediments are not being sourced or transported from non-bare areas, i.e. areas that are not covered by vegetation?
Yeah, sure.
Maybe I'll jump in here and just clarify my question. So I spotted the coefficients that you had that governed the rate of transport. I didn't spot one for non-bare areas, which I assume are areas that are covered by vegetation. So is there an assumption that sediment isn't being blown up from areas that are covered by vegetation?
Right. So that we assume that the urine sediment transport rate here without vegetation. And this urine transport rate was estimated from the Cameron's formula. So yes, that we consider the sediment movement from non-vegetated area to vegetated area. Yes.
Thank you.
Is that the answer to your question?
Yeah. I was.
Okay, thank you.
So I guess the vegetation acts as more of a stabilizing factor, and it's not really sourcing a lot of the sediments that are being transported to the back beach. Cool. Thank you.
So you mean this direction when the winds blow from the land?
I just because the vegetation coverage did seem a little bit variable, and I had wondered that if you had the case where there was sediment that was further towards the sea being sourced from that area, if you had a patch of vegetation, are you assuming that the vegetation is basically prohibiting sediments from being blown up onto the back beach? That contribution from the vegetated areas is negligible?
So your question is about our study site?
Sorry?
Your question is about our study site or any other the beaches?
Just trying to understand under what circumstances you assume that sediment is mobile. And
okay, so being,
yep.
Okay, this area, there is no vegetation. So, that the urine sediment transport is fully developed. And I think that as I explained in my presentation that, the distance from the seaward limit of the investigation area to the wave, the average wave run-up limitation is 40 meters. And we think that the 40 meters is enough to develop the urine sediment transport. So that at the seaward limit of the investigation area, we assume that the fully developed urine sediment transport, that sediment are fully developed enter through this seaward limit of the investigation area. And some of them are trapped here because of the vegetation in summer.
Great, thank you.
Okay.
Okay, so the second question is from Kristen, and it says, the equilibrium and non-equilibrium sediment transport rates also seemed not to match the measurements didn't seem to match the measurements you had. How could this impact your model?
Wow. Yes, you're right. Maybe this one? Oh no. You're right. You're right.
You had this one here. Yeah, it went by really quickly, so I was just trying to read it, and yeah, they didn't seem to match your measurements. So I was wondering if you could explain a little bit more, maybe the measurements on here and how that played into your model, if possible. Thanks.
Okay, actually, that I did this the calculation that about 20 years ago, and this measured the urine sediment transport rate was estimated using the assumption that urine sediment transport rate was 0 at the landward limit of that investigation area. So probably that the real measured real urine sediment transport rate would have been larger than this one shown in these figures. But anyway, that we cannot reproduce that the cross-check variation of that measured urine sediment transport rate. So, well, yeah, I think that such kind of that discrepancy between the measured and the calculated values, reflects that error in our calculation of the volume change rate. yes, that still that there are plenty of the rooms for the improvement of that calculation for the volume change in the backshore.
Okay, we'll move on to the next question. And this is from Hai Jiang, and it says, do you think the calibration could be longer and the validation could be shorter? This may be better for your model. And the second one is 0.2 millimeter sand in the model may be large. Aeolian sand should be smaller than sand in the water.
Okay. Well, but first from the second for the second question, yes, 0.2 millimeter is a little bit large. Probably here 0.1607, but such aeolian sediment transport rate can be compensated by the K value. I think. Sorry, here K value. I think so. Probably that the difference between the 0.16 and 0.2, well, may do not have that the big difference in the calculation result. I think. And the first question is that, well, the calculation and the validation, the period, right?
Yes.
So that, oh, Ryu-san, nice to see you again. And your proposal is to say that more longer calibration period and a more shorter validation period, right?
Yes.
Yes, yes, probably.
Yes, now in your calculation, you separate the calibration and the validation at the same time period, for the same time period. I think in general, we use a longer calibration period, but short period for validation. Maybe that will improve your model somehow, or improve the calibration for the three coefficients.
Yeah, okay. Thank you for your comments. That okay, we'll try. But when we did that, we think that 50-50 would be fair to validate, to evaluate model performance. But yes, we'll try that 70% for the calculation and 30% at the validation. Yes, for the machine learning techniques, sometimes such kind of that 70% or 30% is used. Yes, thank you very much for your comments.
Okay, so the next question is from Anna, and it is, what about elevation? Does elevation change as sediments accumulate? Could it be that once a certain volume elevation is achieved, there is no room capacity to accumulate more sediments? Or maybe there is no longer a source?
You're right. So that such kind of that influence can be predicted, including the beach slope. I think not only the room, maybe that the beach slope is more important because at upper world still there is a room. So I think that the beach slope is more important. But well, in the future we'll think of that. Yes. Thank you very much.
Okay, so the next question is, vegetation areas are separated north side and south side. But this research focused on cross-shore sediment transport.
Yeah, that's right.
How the areas of vegetation affected the results?
Actually, sorry. Well, when the winds blow from the north, we use that the area of the vegetation in the north side of the survey area. And when the winds blow from the south side, we use that the ratio for the south side. Well, so that such kind of difference, north and the south, we included in the model. However, well, now I think that, well, the condition of the vegetation is changed at the survey area. So there is some influence of the longshore aeolian sediment transport rate on the beach flora change. Yes, there may be some influence, but to consider that such kind of influence, it's might be very tough, very tough. But yes, I think of that. I think of that. Okay, thank you.
Alrighty, so we've worked through all of the questions that were typed into the chat. So I'd now like to open the floor to if anybody else would like to ask any questions directly or have any comments they'd like to say about the talk we saw today.
Okay, so if no one has any more questions, okay, could you just join me in thanking Yoshi for a very interesting talk? This was great. Thank you very much. And remember that we have another seminar in 2 weeks with Oscar Ferreira from Portugal talking about risk assessment. So thank you very much, and a real pleasure to have had Yoshi KURIYAMA here today. Thank you.
Thank you very much. It's my pleasure. Thank you.
Great.
Yoshi.